Why does Earth enter an ice age every 1,000,000 years? We move through life with a particular belief. We take for granted that the Earth is a warm, welcoming and flourishing planet. We tell ourselves that the frozen caps at the poles are fixed and remote features pale crowns perched on a blue sphere. We trust that the climate we enjoy, the climate that enabled cities to rise, crops to grow, and civilization to form, represents the natural order of things. Yet this belief is deceptive. The world we know today is not the standard. It is an unusual, brief, and delicate anomaly. If you were to pull back your perspective, if you viewed the past 1 million years of this planet's story as a single sweeping timeline, you would witness a reality that looks nothing like the present. You would see a world shaped not by warmth, but by bitter cold. For most of humanity's existence, the Earth has been a frozen, pale, and unforgiving realm. The massive sheets of ice were not restricted to the polar regions. They were giants that advanced across continents covering North America, Europe, and Asia beneath towering walls of ice, reaching 3-kilometer high. The Ice Age has not vanished. It rests in slumber. The glaciers have not disappeared. They have merely withdrawn, slipping back into the distant reaches of the Arctic and Antarctic, waiting for the call that brings their return. Tonight we are going to listen for that call. We are searching for a rhythm, a concealed pattern that steers the destiny of our world. It is a cycle so vast that a human lifetime cannot perceive it, yet so influential that it determines the rising and falling of seas. Every 100,000 years, like the steady pulse of the cosmos, the Earth freezes, and then, just as predictably, it thaws. This is the enigma of the Milankovitch cycles. It is the tale of how the faint and silent motion of our planet through the darkness of space shapes the future of all living things. It is a tale woven from mathematics, celestial mechanics, and the work of a solitary prisoner who unraveled the secret of the ice while the world outside was consumed by war. We will follow the workings of this immense cosmic mechanism. We will stand upon the ice sheets that once crushed continents. We will look upward and recognize how a subtle tilt, a gentle sway in our planet's rotation, can transform a flourishing landscape into a desolate plain. So before you settle in, take a moment to show your support only if you truly enjoy these explorations. Share where you are watching from and what time it is for you. It is always intriguing to see the wide range of people joining us from across the globe. Now dim the lights. Maybe let a fan run to create a soft ambient hum, and let us slip together into tonight's journey. To discover the rhythm of the past, we must travel to the quietest place on Earth. We must venture to the lonely heart of the Antarctic Plateau. Here at the remote Russian outpost known as Vostok, temperatures can plunge to -89 degrees Celsius. It is so cold that a single breath freezes instantly and falls as tiny crystals of ice. It is a blank, white emptiness that appears identical in every direction. But the true significance of Vostok lies not in what you can see on the surface. It lies far beneath. Under the feet of the researchers stationed in this desolate place rests an ice sheet almost 4 kilometers thick. This ice is not a single uniform block. It is an archive. Snow in Antarctica never melts. It accumulates relentlessly year after year, layer after layer. As new snow settles, its weight presses down on the older layers, compressing them, forcing them to transform from soft white powder into solid blue transparent rock. During this transformation, something invaluable is preserved. As the snow becomes ice, it traps tiny bubbles of air between its crystals. When the ice hardens, those tiny pockets become sealed forever. They turn into microscopic capsules of time, preserving samples of the Earth's atmosphere from the precise moment each layer of snow settled. If you descend 100 meters, you are inhaling air that dates back to the era of the Roman Empire. If you drill down 1 kilometer, you encounter air from a period long before human civilization emerged. And at Vostok, they went even deeper. For decades, enduring conditions that pushed human resilience to its extreme boundaries, teams of researchers carved a narrow shaft straight into the core of the ice sheet. They extracted long cylinders of ice known as ice cores, stretching more than 3,000 meters. When examined in a laboratory, a core resembles an elongated polished rod of glass. Yet look closer, and you will see them countless suspended bubbles. These bubbles hold the ancient breath of the planet, containing carbon dioxide, methane, and dust from a world that has vanished. By delicately crushing these samples in a vacuum and studying the gases released, we are able to experience the atmosphere of the distant past. The Vosto core transported us 400,000 years backward in time. Later cores, such as those drilled at Dome C, carried us 800,000 years into the past. It stands as the most complete, continuous, and detailed record of climate ever uncovered. It is a vertical chronicle preserved in deep cold, untouched by decay, untouched by erosion, waiting for us to learn its language. And when researchers finally assembled the information from these cores, when they charted temperature and carbon dioxide over nearly 1 million years, they did not find a straight trajectory. They did not find randomness. They discovered a pulse. The data from Vosto carried no ambiguity. Its precision was startling. When scientists graphed Earth's temperature across the last 800,000 years, the line did not drift without purpose. It did not resemble the wild fluctuations of weather. It resembled a mechanism. The pattern formed a repeating serrated curve. This is what we call the sawtooth pattern. Picture the jagged edge of a saw blade. One side is long and gentle, the other is abrupt and sharp. The long, gentle slope marks the descent into freezing. For about 90,000 years, the planet cools steadily and persistently. The ice sheets expand slowly, century after century, encroaching onto the continents. Global temperatures fall into the depths of a glacial maximum. Then comes the sudden shift, the sharp vertical side of the pattern. In what amounts to a geological instant, perhaps only 10,000 years, temperatures surge upward. The ice recedes. Vast regions flood. The climate leaps from deep freeze to a warm and stable interglacial phase, much like the one we inhabit today. And almost immediately after this warmth, the slow downward slide toward cold begins anew. This cycle repeats again and again 8 times over the past 800,000 years. Roughly every 100,000 years, the planet inhales the cold and briefly exhales the warmth. It is a rhythm steady enough to resemble a heartbeat. This revelation transformed our understanding. It showed that the ice ages were not random occurrences. They were not triggered by unpredictable volcanic events or stray cosmic impacts. They followed a cycle. They were unavoidable. Something was orchestrating this pattern, something powerful enough to chill an entire world, yet exact enough to operate with a timing so regular it could be measured like a clock. But the source of this rhythm was not found on the Earth itself. No one can locate a 100,000-year cycle in tectonic plates. It does not arise from ocean circulation. The planet is far too chaotic to maintain such precise order. To identify the maker of this cosmic clock, we had to look beyond the Earth entirely. We had to wait for a Serbian mathematician confined in a prison cell and contemplating the flicker of a candle to recognize that the solution rested in the silent mathematical harmony of the heavens. The key to the mystery of the ice did not come from a glaciologist standing on a frozen ridge. It came from a mathematician locked behind bars. The year is 1914. The world is spiraling into the turmoil of the First World War. While armies marched and empires collapsed, a Serbian engineer and mathematician named Milutin Milankovic was seized by the Austro-Hungarian authorities. Taken from his honeymoon, he was held as an enemy foreigner and eventually confined in Budapest. Yet while the world outside his window tore itself apart with artillery fire and mustard gas, Milankovic accomplished something remarkable. He turned away from the chaos unfolding in the present and directed his attention deep into the quiet archives of the past. A small mercy was granted to him. He was permitted to work inside the library of the Hungarian Academy of Sciences. There he sat day after day while Europe burned, equipped only with a fountain pen, piles of paper and a slide rule. He set himself a task that even now seems nearly impossible. He resolved to compute the climate of the Earth for the last 600,000 years. He had no ice cores. He had no supercomputers. He lacked the geological records we depend on today. All he possessed were the fundamental laws of physics. Milankovic believed that the climate of the Earth was not governed by randomness. He believed it functioned like a machine powered by the energy of the sun, and if it was a machine, then its motions could, in principle, be calculated. He reasoned that if he could determine the precise position of the Earth relative to the sun at every moment throughout the distant past, he could then determine exactly how much solar energy reached the planet at any latitude. It was a calculation of overwhelming complexity. He had to consider the gravitational forces of Jupiter and Saturn, the shifting distribution of mass within the Earth, and the delicate mechanical interactions of the entire solar system. He worked alone for years. He filled thousands of pages with dense handwritten trigonometric expressions. In his mind, he lifted the Earth from its orbit and spun it backward through time. He was assembling a mathematical spectre of the planet, As the numbers began to settle into place and the pages accumulated, a pattern slowly revealed itself. It was not a chaotic scribble, it was a wave. Milankovitch recognized that the Earth does not move through an empty void. It journeys through a web of unseen influences. These forces, these gravitational pulls from distant giants, were gradually and rhythmically reshaping the motion of our planet. He had uncovered the gears of a cosmic timepiece. Before, Milankovitch geology focused almost entirely downward. When researchers sought explanations for climatic shifts, they searched for answers in the mud. They examined volcanoes, drifting continents, and the circulation of the deep oceans. They assumed that the driving mechanisms of Earth's history were contained solely within the Earth. They regarded the planet as a sealed system, a solitary vessel drifting through space. Milankovitch dismantled this assumption. He understood that to explain the heat and cold of the planet, one cannot look only at the patient. One must examine the room in which that patient stands. He recognized that the Earth is not a closed system. It is fueled by one external engine, the sun. Every spark of energy that powers the winds, moves the rivers, and nourishes the forests originates from that star. Hence, the temperature of the Earth depends on a simple question: how much sunlight reaches us and where does it land? For a long time, people believed that this relationship remained constant. The sun burns steadily, the Earth orbits it, the seasons pass. But Milankovitch identified the flaw in this fixed view. He realized that the solar system is not an empty chamber. It is a crowded arena. We share this space with the giants, Jupiter and Saturn, immense gas worlds, with gravitational fields far surpassing our own, and with smaller rocky companions like Venus and Mars. Gravity is an invisible tether. It is faint yet boundless. It stretches across the emptiness. Thus, as the Earth moves around the sun, it does not trace a perfect isolated path. It is pushed, it is pulled, it is gently shifted by the gravity of Jupiter and nudged by the passage of Saturn. These forces are subtle. In a single year they amount to almost nothing, but time magnifies all things. Over tens of thousands of years, these faint, rhythmic gravitational pulls accumulate. They begin to distort the trajectory of our world. They begin to lean it. They begin to make it sway. Milankovitch understood that the Earth's location in the cosmos is never fixed. It is in motion, and this motion alters the way sunlight reaches the ground. It does not necessarily change the total amount of heat our planet absorbs, yet it shifts where that warmth arrives, and most importantly, when it arrives. He uncovered 3 separate motions, 3 distinct mechanisms within a celestial timepiece, each turning at its own pace, and each influencing the climate in its own particular manner. When these mechanisms synchronize, they can redirect the Arctic sun just enough for winter snow to endure through summer, allowing ice to accumulate and envelop the world. We often imagine the solar system as a flawless, orderly construct, a perfect machine where planets glide along unseen rails, distant and unaffected by their neighbors. But gravity recognizes no borders. Its reach is limitless. It weakens over distance, yet it never fully fades. In the silent emptiness of space, Earth does not travel alone. It moves among giants. Far beyond the orbit of Mars lies Jupiter, a world so immense it contains more than twice the matter of all the other planets put together. It is a failed star, an enormous sphere of gas whose gravitational pull extends across hundreds of millions of miles. Even farther is Saturn, another enormous presence shaping the outskirts of the solar system with its powerful attraction. As Earth speeds around the Sun at 67,000 miles per hour, it repeatedly passes through the gravitational wake of these titans. Each time we sweep past Jupiter, we feel a pull. It is faint, barely noticeable, a gravitational murmur. If it occurred only once, it would be meaningless. But it happens over and over, relentlessly, across billions of years. It resembles pushing a child on a swing. A single gentle push hardly matters, but when every push arrives at just the right moment, the energy builds. The arc rises higher, the motion grows more dramatic. This is the principle of orbital resonance. Because of these continuous rhythmic pulls from Jupiter and Saturn, Earth's route through space does not remain fixed. It shifts, it expands and contracts. The orbit stretches outward, becoming elongated and oval, drawing us millions of miles away from the sun's warmth. Then gradually, under new gravitational arrangements, it contracts again toward a nearly perfect circle. Earth spins like a top yet under the tug of the moon, and the sun, that spinning top, begins to lean and wobble. Its axis dips and lifts. This is the cosmic mechanism at work, a complex, unpredictable, and mesmerizing dance shaped by gravity. Earth is continually influenced by both the sun and the gas giants, a small rocky traveler carried along in a vast gravitational current. And Milankovitch recognized that this grand dance can be separated into three specific motions, three core mechanisms that govern the climate of our planet. The first mechanism is the broadest, the slowest, and the most influential. It is the shape of Earth's orbital path. This first mechanism in the celestial clock is the slowest of all, yet it establishes the rhythm of the entire Ice Age cycle. It is called eccentricity. In our imagination, and in the illustrations taught during childhood, Earth's path around the Sun is shown as a perfect circle, steady and unchanging. But this is only a simplification. The actual orbit is not circular. It is elliptical, an oval resembling a circle that has been gently compressed. And this form is not permanent. It changes gradually. Over an immense cycle of roughly 100,000 years, the gravitational influence of Jupiter and Saturn slowly pulls at Earth, stretching its path. The orbit shifts from a nearly perfect circle into a long, extended oval. And then, with equal slowness, it returns to its earlier shape. This is the stretch. Why is it important? Because an orbit is not merely a trace through empty space. It represents distance. When the orbit is circular, Earth stays at a stable, comfortable spacing from the Sun throughout the year. Heat remains consistent. But when the orbit elongates, when eccentricity increases, Earth is pushed far into the cold, dim reaches of space before curving back inward. At the farthest point of this extended path, we travel millions of miles farther from the Sun than normal. It is like standing beside a fire and then stepping back twice. The total solar energy reaching Earth diminishes. Winters grow a little longer. Summers grow a little weaker. The planet begins to receive less incoming energy, and here lies the essential point. This cycle, the gradual stretching and relaxing of the orbital path, requires exactly 100,000 years to run its full course. It aligns perfectly with the rhythmic signal revealed in the ice core, records the unmistakable sawtooth pattern from the frozen archives. The advance and retreat of the vast ice sheets rise and fall in flawless harmony with the elongation of our orbit. When the Earth drifts farther from the Sun, ice expands. When the orbit settles back into a more circular form, the ice retreats. This is the dominant pattern. The 100,000-year pulse of the glacial eras is quite literally a reflection of our shifting distance from the star that sustains our climate. Yet distance on its own cannot lock a world in ice. The cold requires assistance. It must know precisely where to deliver its blow. This is why we turn to the second mechanism. The first mechanism, eccentricity, determines how far we stand from the source of heat. But the second mechanism governs something far more delicate and far more consequential. It governs the angle at which sunlight reaches our world. This is obliquity, the tilt of the axis. To grasp this, imagine the Earth not as a motionless sphere on a tabletop, but as a spinning toy top. When the top spins rapidly, it stays upright. As it slows or as unseen forces disturb it, it begins to dip. It sways gently in a slow, mesmerizing oscillation relative to the ground. Our planet behaves the same way. It spins at 1,000 miles per hour, floating in the vacuum, and it performs this subtle, nodding motion. We are usually taught that the Earth is tilted at 23.5 degrees relative to the Sun. This is the crucial angle. It is what creates the seasons. When the northern hemisphere leans toward the Sun, summer arrives. When it leans away, winter takes over. It is the motor that drives our annual cycle. But this value of 23.5 is not fixed. It is only our current position in a long pattern. Over a span of 41,000 years, the Earth gently rocks back and forth. The tilt shifts from a mild 22.1 degrees to a pronounced 24.5 degrees. It appears insignificant, a small change of just 2 degrees. On a simple measuring tool, the difference is hardly noticeable. But on a living planet, it marks the boundary between fertile landscapes and frozen wilderness. This leads us to the central puzzle of the ice ages. If you were to ask someone what triggers an ice age, they might respond with extremely cold winters. It feels intuitive. Harsh winters should freeze the world. But Milankovitch understood this was incorrect. He recognized a deep atmospheric principle. Bitterly cold winters do not build glaciers. In fact, extremely cold winters tend to lack moisture. They leave the ice sheets without the snowfall they need. The true driver of an ice age is not the winter season. It is the summer. Think about how a glacier forms. A glacier begins as snowfall. Each winter, snow blankets the high northern regions of Canada, Scandinavia, and Siberia. This is ordinary. The decisive moment arrives in July. When summer comes, its task is to melt that snow. It must clear the surface before the next winter arrives. If the summer is warm, the snow disappears and the land remains uncovered. But what takes place when the Earth's tilt is minimal? What happens when the angle decreases to 22.1 degrees? It means the summer sun never climbs high in the sky. It lingers near the horizon. Its rays become faint, angled, and weakened as they pass through more atmosphere. It provides daylight but minimal warmth. Under these conditions, the summer fails in its duty. Sunlight reaches the ground, but it cannot eliminate the previous winter's snow. The snow persists. It remains through June, July, and August. It sits unmoving, bright and reflective, bouncing the feeble sunlight back into space. Then September arrives, and with it the next winter. New snow settles atop the old snow that never melted. This is the birthplace of an ice age. It is the remnant of a winter that the weakened summer could not erase. Year after year, this surviving layer builds. The weight of new snowfall compresses the layers beneath. The snow crystals collapse. They lose their trapped air. They shift from a soft white powder to a coarse material known as firn. And then, under tremendous pressure, they bond into solid blue ice. This process repeats for thousands of years. The mass grows taller. It begins to move under its own weight. It fills the valleys. It overtops the peaks. This is the influence of the axial tilt. It is the 41,000-year cycle that governs the intensity of the seasons. When the tilt grows greater, the seasons become extreme and scorching summers erase the ice. When the tilt decreases, the seasons soften and cooler summers give the ice a chance to endure. This mechanism, this gentle rocking of the planetary cradle, decides whether snow vanishes or rises into a monument to the cold. Yet there is one last mechanism, one that moves more quickly, behaves more strangely, and shifts more chaotically than the others. It is a wobble that alters not only the seasons but the very stars overhead. The first mechanism stretches the orbit, the second tilts the axis. But the third is the most disorienting of all because it redefines our position among the stars. This is precession the wobble. Anyone who has ever watched a spinning top closely knows it never remains perfectly still. As it spins, the handle slowly traces a loose circular path in the air. It glides. The Earth performs the same motion. At this moment, the North Pole is aimed directly at a particular star, Polaris, long known as the North Star. It has served as a cosmic anchor, a guiding point for sailors across thousands of years. We often assume it is fixed forever. It is not. Because the gravitational pull of the Sun and the Moon tugs on the bulging equator of the Earth, our axis twists gradually. The North Pole is describing an enormous circle through the sky. 12,000 years ago, people did not raise their eyes to Polaris. They gazed instead at a brilliant blue-white star named Vega. 12,000 years from now, future generations will look up and see Vega once more. By then, Polaris will be nothing more than another drifting star. This entire cycle lasts about 23,000 years. It is the quickest hand on the cosmic clock. But why would the direction of the axis matter for climate? Why does it matter which star the pole points toward? It matters because the Earth's path around the Sun is not perfectly circular. Recall the first mechanism, the stretch. Our planet has a point in its orbit where it moves closest to the Sun and another where it travels furthest away. Precession determines which season falls on each side of that orbit. This is essential. At present, by a fortunate cosmic coincidence, the Northern Hemisphere experiences winter when the Earth is closest to the Sun. This makes our winters a little gentler than they would otherwise be. We are nearer to the heat during the coldest months, but the wobble continues to shift. In roughly 10,000 years, the axis will reverse its orientation. The Northern Hemisphere will enter winter when the Earth is at its furthest distance from the Sun, deep in the cold of space, and it will enter summer when it is closest to the blazing heat of the star. This produces a rhythm of extremes. When precession lines up precisely with eccentricity, it creates a superseason. It can make winters savagely cold and summers fiercely hot, or as the cycle continues, it can reverse the pattern, producing gentle winters and cool summers. And as we have already seen, cool summers hold the key. When the wobble aligns just right, it places the Northern Hemisphere, home to the vast land masses of Canada and Siberia, in a position to receive the smallest possible amount of summer sunlight. This deprives summer of the energy required to melt accumulated snow. This is the third mechanism, the fine-tuner, the frequency shifter, that magnifies or cancels the effects of the other two. Milankovic finally possessed all the components. He had the stretch lasting 100,000 years, the tilt lasting 41,000 years, and the wobble lasting 23,000 years. On their own, they are only gentle pushes. But Milankovic recognized that these cycles interlock, they intertwine, and every so often, like the tumblers of an immense cosmic lock slipping into alignment, they fall into the same configuration. When this happens, they open the path to ice. Individually, these forces are weak. A slightly elongated orbit alters sunlight by only a fraction of 1%. A reduced tilt cools summer by barely a degree. A wobble shifts the seasonal calendar by only a few weeks. Alone, they are insignificant, faint background murmurs in the solar system. But Milankovic understood that time behaves like a weaver. It gathers these separate strands, the 100,000-year stretch, the 41,000-year tilt, and the 23,000-year wobble, and it braids them into a single pattern. Most of the time, these cycles oppose one another. The orbit may be pulling us away from the sun, but the tilt may be high, bringing hot summers that melt the ice. They cancel one another, keeping the climate steady and the planet green. Yet once every 100,000 years, everything locks into alignment. The hidden tumblers of a vast cosmic mechanism snap together. It is a brief interval of constructive interference, a rare combination that produces a perfect wave of cold. Picture it unfolding. First, eccentricity reaches its peak. Earth's orbit stretches into a long, narrow ellipse, pulling the planet millions of miles farther from the blazing heat of the sun. Second precession shifts the orientation of the axis so that the northern hemisphere enters summer precisely when Earth is at the furthest and coldest point of that elongated path. The summer sunlight is faint and distant. Third, obliquity declines. The planet stands nearly vertical. The axial tilt reaches its minimum, causing that weak, faraway summer sunlight to strike the high northern latitudes at a shallow grazing angle. It is a triple strike. Distance, timing, and angle work together to drain heat from the north. Solar energy reaching the Canadian Arctic and the Scandinavian mountains plunges dramatically. It falls below the critical limit. Winter snow no longer melts during summer. It endures. It waits for the next winter and then the next. Milankovic sat in confinement and computed these patterns by hand. He sketched a curve predicting exactly when such alignments had occurred throughout history. He foresaw the ice ages long before anyone bored the first ice core. He recognized the mathematical certainty of cold. But a problem remained, a gap in the logic he could not ignore. When the calculations are done, even this flawless alignment of orbital conditions reduces solar input by only a modest amount. It is meaningful, yes, but theoretically insufficient to freeze an entire world. It cannot explain ice sheets 3 kilometers thick. The equations indicate a slight cooling. Geological evidence shows a planet transformed into a frozen wilderness. Something was missing. The orbital cycles provided the spark, but not the explosion. Some earthly mechanism had to seize that faint cooling signal and magnify it. Something within the planet itself had to take a quiet whisper and turn it into a deafening roar. The mathematics were correct. The cycles matched. Milankovic had traced the very pulse of the solar system, yet something invisible in the system created a discrepancy that haunted the theory for years. When physicists estimated the actual heat loss produced by these orbital shifts, the values were unimpressive. Even in the extreme scenario with tilt-reduced axis, wobble-aligned, and the orbit fully stretched, the drop in solar energy reaching Earth remained surprisingly small. It resembled lowering a dimmer switch by a barely noticeable fraction. Such a reduction might produce gentle cooling, a slight temperature decline in the Arctic, perhaps a somewhat extended winter. It should not have entombed North America beneath 3-kilometer thick glaciers. The contradiction was stark. Orbital cycles delivered a whisper, while the climate record showed a shout. The planet reacted with an intensity far beyond what the decreased sunlight could explain, as if a light touch on the brakes sent a car skidding wildly off the road. This pushed scientists toward a profound understanding. Earth is not a passive sphere. It is not a lifeless object that merely absorbs whatever warmth the sun provides. Earth behaves like an active system. It possesses internal mechanisms, concealed levers, and powerful self-reinforcing processes. The orbital cycles serve only as the initial trigger. They turn the key, but the true engine that drives an ice age lies within the planet itself. These internal processes are known as feedback loops. They are the systems that take a minor change and amplify it, doubling or tripling it until it becomes an accelerating force. Milankovic identified the rhythm. To uncover the cause of the deep freeze, we must understand how the planet transformed that faint celestial cue into a force large enough to reshape continents. Earth relies on two dominant amplifiers, two mechanisms that intensify cooling into full glaciation. One arises from light, the other from air. And the first amplifier behaves like a mirror. It emerges from a straightforward principle of color. Picture yourself crossing a dark asphalt lot on a scorching summer day. The surface burns, radiating heat through your shoes. Now imagine stepping onto bright white concrete. It feels cool. This illustrates the albedo effect. It measures how much light a surface reflects. Dark regions, such as deep blue oceans, green pine forests, and brown soil, are absorbers. They take in sunlight, convert it into heat, and warm the surrounding air. A planet blanketed in forests and oceans tends to remain warm. White surfaces act in the opposite way. Snow and ice behave like natural mirrors. They do not take in warmth, they repel it. They send the sunlight straight back through the atmosphere and out into the cold emptiness of space. A world covered in ice is a world that resists warmth. This sets off a hazardous chain reaction. When the Milankovitch cycles align, when the orbit stretches and the axial tilt decreases, northern summers lose their strength. Small remnants of snow in the Canadian highlands or the Scandinavian mountains manage to persist through July and August. At first, these remnants seem trivial, tiny white specks on a dark landscape, yet their power lies in their brightness. They reflect the weakened summer sunlight. The air directly above them cools. This slight cooling helps the patch endure and encourages new snow to gather at its perimeter. The white area expands. As it grows, it functions like an enlarging mirror. It reflects even more sunlight. The surrounding region becomes colder. As temperatures fall, snowfall increases. With more snowfall, the mirror grows wider. This is the ice albedo feedback. It behaves like a prediction that fulfills itself. Once the snow cover spreads beyond a crucial threshold, perhaps extending across the Hudson Bay or the Baltic Sea, the chain reaction becomes irreversible. The planet stops resisting the cold and begins producing it. The massive ice sheets of the northern hemisphere were far more than frozen water. They were shields the size of continents. During the peak of the last ice age, the immense whiteness covering North America and Eurasia reflected vast amounts of solar energy away from Earth. The planet was essentially turning its face from the flame. It was pushing away the very energy that could have warmed it. This feedback loop clarifies how a slight decrease in sunlight can produce a local freeze. It explains how the ice advanced. But the ice ages were not limited to one region. They were worldwide. When the northern hemisphere froze, the southern hemisphere followed. The tropics dried. The entire planet cooled together. A reflective shield in Canada cannot chill the Amazon rainforest. For the cold to envelop the entire globe, Earth required a second amplifier. It needed a system capable of transmitting the message from the northern ice sheets to every region. It needed to alter the atmosphere itself. The mirrors of ice clarify why the North froze, but they do not explain why the entire planet joined it. When glaciers swept through Canada, the Amazon rainforest cooled as well. The deserts of Africa shifted. The whole planet from one pole to the other entered a coordinated chill. A local reflective surface cannot achieve this. To lower global temperatures, the atmosphere must be changed. The protective veil must be thinned. This leads to the second amplifier, the thief. That thief is the ocean. To understand this process, picture a bottle of soda, leave it under the hot sun, and it quickly loses its fizz. The gas escapes. Keep it ice cold, and the gas remains trapped inside. Cold water holds more dissolved gas than warm water. This is a basic rule of physical chemistry. As the Milankovitch cycles triggered those first faint hints of cooling in the north, and as the white mirrors of ice began reflecting sunlight, the temperature of the world's oceans dropped. As the water cooled, it became greedy. It began to draw in gas. The oceans started extracting carbon dioxide from the air. Billions of tons of heat-trapping gas were pulled from the atmosphere and absorbed into the waves. As the carbon dioxide concentration in the air decreased, the greenhouse layer thinned. The planet lost its ability to retain warmth. This caused further cooling, which chilled the oceans even more, allowing them to absorb still more gas. It became a downward spiral into deep planetary cold. Yet the ocean possessed another, even more active strategy for burying atmospheric carbon. It used life itself. As the ice sheets expanded on land, they scraped the bedrock into fine, mineral-rich dust. Winds driven by the glaciers swept this dust out over the oceans. It acted as a gigantic infusion of nutrients. Surface waters erupted with life. Phytoplankton, microscopic plant organisms, bloomed in immense swirling clusters visible from space. These tiny beings consumed the remaining carbon dioxide from the air to build their bodies, and when they died, they did not decay near the surface. They sank. A steady snowfall of dead carbon drifted into the crushing darkness of the depths. There, it accumulated on the ocean floor, trapping that carbon for thousands of years. The ocean had effectively stolen the atmosphere's insulation. This is why the Vostok ice cores show carbon dioxide and temperature moving in perfect unison. When carbon dioxide falls, temperature plummets. The orbital cycles lit the first spark. The ice sheets acted as vast reflective surfaces, yet it was the ocean quietly absorbing the sky's warmth that transformed a regional cold spell into a planet-wide ice age. The conditions were now perfectly aligned. The trigger, the mirror, and the silent thief moved together as one. The world stood on the brink of a long, frozen era. The moment had arrived. The orbit had pulled the trigger. The reflective surface was casting sunlight away, and the ocean was locking the warmth beneath its surface. At that point, the continent itself began to change form. Many people imagine an ice age as a period of endless storms, a constant barrage of white chaos. In reality, the rise of the massive ice sheets was likely something more subdued and far more unsettling. It was a slow and unstoppable suffocation. It started at higher elevations. On the Keewatin Plateau in Canada and throughout the ranges of Scandinavia, snowfall simply refused to melt. Season after season, the accumulation grew 10 feet, 50 feet, 100 feet. Once the layers reached a critical depth, the physical nature of the snow transformed. The crystals buried beneath the weight of the newer layers were crushed, compressed by the tremendous load pressing down from above. They bonded together, forcing out the air and shifting from soft white powder into a dense blue substance that behaved like solid plastic. The ice began to move. It crept forward like a river made of slow-moving syrup. Drawn downhill by gravity, immense lobes of ice pushed outward from the highlands, flowing into lowlands, engulfing forests and filling ancient lake basins. These formations were nothing like the small glaciers that cling to mountains today. They were continental-scale domes of ice that sculpted their own landscapes. The greatest of them was the Laurentide ice sheet. It expanded until it covered almost all of Canada and the northern portion of the United States. It consumed the Great Lakes. It buried the locations where Chicago, New York, and Boston now stand. At its center above Hudson Bay, the ice was not a thin shell. It rose into a dome more than 3 kilometers high. Picture yourself at the foot of a towering wall of ice, stretching into the stratosphere, rising higher than the Rocky Mountains. It was so massive that it altered the rotation of the planet. It blocked the jet stream itself, forcing the winds to reroute and reshaping the climate across the entire northern hemisphere. In Europe, the Fennoscandian ice sheet advanced from the north, overwhelming the British Isles and Scandinavia and pushing as far south as Berlin and Moscow. These were the pale giants. They were immense, frigid, and without emotion. They scraped the surface of the planet down to bare stone, behaving like colossal sheets of sandpaper, erasing river systems and carving the very landscapes we travel across today. And as they expanded, another change took place. Their weight increased, so much in fact that they began to deform the crust of the planet. Water carries weight, a full bucket reminds anyone of that. 1 cubic meter of water weighs a ton. Now picture an expanse of frozen water stretching thousands of miles and stacked 3 kilometers tall. The force is staggering. It is a load so tremendous that the crust of the Earth, which we often imagine as solid and unmoving, could not resist it. It yielded. We tend to picture the ground beneath us as a firm platform, but on geological timescales, the crust behaves more like a raft riding on a deep, viscous ocean of molten mantle. Place an enormous weight on a raft, and it sinks. Under the crushing mass of the Laurentide and Fennoscandian ice sheets, the land masses of North America and Europe literally subsided. Solid rock was pushed downward nearly 1 kilometer into the mantle. The ice carved out its own depressions. It reshaped landscapes that once curved outward into deep basins. Hudson Bay in Canada remains a lingering imprint of that pressure, a sunken mark left by the core of the ice dome where the weight was greatest. This descent did not happen suddenly. It was the slow concession of stone to an overwhelming burden, and the return to equilibrium has been equally slow. This is one of the most haunting remnants of the ice ages. The ice disappeared 10,000 years ago, yet the land still retains the memory of its weight. It continues to rise. This process is known as isostatic rebound. Even now, while you hear these words, the ground in Scandinavia and northern Canada is lifting. It is emerging from the sea at a rate of about 1 centimetre each year. The old Viking shorelines now sit far inland, raised high above the ocean by the gradual and lingering recovery of the crust. The planet is still recovering from a deep bruise. Yet while the continents were sinking beneath the ice, the rest of the world was undergoing changes just as dramatic. The water that formed these towering white structures had to originate somewhere. The ice sheets did not appear out of thin air. They drew their mass from the oceans. As the frozen layers thickened, the seas diminished. The layout of the planet was being rewritten. To create an ice mountain 3 kilometre high, the ocean had to be drained. The sheer volume of water trapped inside the Laurentide and Fennoscandian ice sheets was astonishing. It was enough to drop the global sea level by 120 metre, equivalent to the height of a 40-story skyscraper. If you were standing on a shoreline during the last glacial maximum, the waves would not be at your toes. The sea would be missing entirely. It would appear only as a distant blue ribbon on the horizon, lying miles away across a windy, salt-crusted plain. The familiar geography of school globes, the recognizable outlines of continents vanished. The British Isles were not islands at all. They formed the elevated edges of a massive, low-lying extension of Europe. You could trek from London to Paris or from Amsterdam to Newcastle without touching a drop of water. You would be walking across Doggerland, a fertile, grassy tundra alive with mammoth and reindeer, a region now submerged beneath the cold waters of the North Sea. Farther East Asia and North America were not divided by the sea. The Bering Strait, that slender channel between Russia and Alaska, became a broad, solid expanse known as Beringia. It functioned as an intercontinental thoroughfare, a sweeping grassland corridor stretching thousands of kilometres that allowed life to move freely between continents. The planet itself had more exposed surface. Continental shelves rose into open air. The world was drier and dustier. With so much water locked in frozen sheets, global rainfall collapsed. The flourishing rainforests near the equator retreated into isolated refuges replaced by expanding dry savannas. The world was not only frigid, it was parched. Yet, in this expanded and dehydrated landscape, life adapted. It did not merely survive the cold. It used the revised map to disperse. The ice had sealed the northern passages, but falling seas created new pathways for extraordinary migrations. The ice sheets acted as barriers, towering pale fortifications blocking the northern skyline. But by draining the seas, they unintentionally fashioned connections. For the living world, the Ice Age was not a period of immobility. It was an era of remarkable movement. The planet was colder, certainly, but it was also linked in ways unfamiliar today. The separation of continents faded. The great land masses of Eurasia and the Americas, normally divided by the roiling, freezing waters of the Pacific, were joined by the Bering Land Bridge. Calling it a bridge understates its scale. It was a subcontinent, a region as wide as modern France, a vanished realm that endured for thousands of years before slipping beneath the waves again. And it was far from a desolate ice field. This is one of the major misunderstandings of the Ice Age. We picture an Earth smothered in deep snow, but with so much moisture trapped in glaciers, the air was intensely dry. In many regions, snowfall was too limited to sustain new glaciers. Instead, a distinct and now vanished ecosystem spread across the northern hemisphere. It was known as the Mammoth Steppe. Picture a continuous grassland stretching from the shores of Spain across the full span of Russia over the land bridge and deep into the Yukon of Canada. A single immense wind-swept expanse of dry, nutrient-rich grass and sagebrush. It was cold, arid and dusty with relentless winds sweeping across it. But during the summers under the round-the-clock daylight of high latitudes, this steppe erupted with life. It supported animal populations comparable to the modern Serengeti. Herds of woolly mammoths perfectly adapted to this frigid, dry realm grazed beside woolly rhinoceroses. Vast groups of steppe bison thundered over the plains, pursued by cave lions and scimitar-toothed cats. It was a land of giants, a Serengeti sculpted by ice. And moving in the shadows of the tall grass, tracking the herds with quiet precision, was the most formidable hunter of all, humans. The Ice Age did not halt human expansion, it hastened it. Lower sea levels revealed coastal pathways. The green passages that opened between ice sheets during brief warm intervals funneled populations northward. For our ancestors, the Ice Age acted as an open invitation. The drying world pushed them out of receding forests and onto broad open plains. The cold demanded ingenuity, pushing them to refine firecraft, sophisticated clothing, and build protective shelters. They journeyed along the Mammoth Steppe. They traveled from Siberia into Alaska, unaware they were crossing between massive continents, simply trailing the grasslands and the animals that sustained them. They lived upon the land bridge as inhabitants, rather than merely as passers-by. Genetic research indicates that human populations may have remained in Beringia for thousands of years. A prolonged pause in this region, enclosed by towering walls of ice to the east and to the west, allowed them to develop into a unique genetic branch that would eventually expand throughout the Americas. The harsh cold acted like a forge. It strengthened both animals and humans, eliminating the fragile and favoring those capable of adapting. For millions of years, this rhythm held steady. Ice advanced oceans receded, pathways appeared, and life migrated. Then the ice withdrew, the oceans rose, the roots closed, and species evolved apart from one another. It was a perfectly repeating pulse. A 41,000-year heartbeat that dictated movement, evolution, and extinction. But eventually, something unusual occurred. The rhythm failed, the cosmic metronome missed a beat. Around 1 million years ago, the long-standing pattern that had governed the planet abruptly changed. Winters lengthened, ice thickened, and the cycle decelerated. For nearly 2 million years, Earth had operated like a reliable mechanism. Deep ocean floor sediments make this pattern unmistakable, steady and unwavering. The planet moved to a 41,000-year cycle. This was the rhythm of axial tilt. As the Earth swayed on its axis, the ice sheets advanced and retreated in almost perfect harmony. It was a world of symmetry. Ice ages occurred often but remained relatively gentle. Warm intervals also appeared often but stayed moderate. It was a balanced and predictable system. Then, close to 1 million years ago, something in that mechanism failed. Scientists refer to this event as the mid-Pleistocene transition, one of the most perplexing enigmas in the history of Earth's climate. Without warning and with no obvious external trigger, the planet's heartbeat slowed. It skipped one beat, then another. The 41,000-year cycle faded. A new rhythm emerged, far longer and far more severe. The cycle stretched to 100,000 years. This shift was not only about duration, it was about force. Under the earlier system, ice sheets behaved like shallow tides sweeping across the northern continents and then withdrawing quickly. Under the new 100,000-year regime, the ice turned aggressive. It became persistent. The glaciers no longer melted simply because the tilt indicated they should. They endured through warmer orbital phases. They grew taller, colder, and heavier, accumulating for 90,000 years at a time, reaching masses and heights that Earth had never witnessed before. And when they finally collapsed, the ending was sudden and violent, producing the jagged sawtooth pattern recorded in the Antarctic ice cores. Here lies the true enigma, the question that continues to trouble researchers. The sun did not shift. The Milankovitch cycles, including the stretch, the tilt, and the wobble, continued unchanged. The cosmic clockwork remained precise. The signal from space stayed the same, yet the Earth stopped responding. It ceased reacting to the strong, clear influence of axial tilt and instead aligned itself with the far weaker, far more delicate cycle of orbital eccentricity. It was as if a radio abruptly ignored a loud, crisp broadcast on its primary channel and tuned itself to a faint whispering static, amplifying that dim signal until it overshadowed all else. Why did this happen? Why did the planet plunge into deeper, longer, harsher winters? Why did the ice become increasingly resilient? The explanation, as we now suspect, does not come from the sky but from beneath the ice. It lies in the friction between glacier and stone. The planet altered the surface upon which its ice rested. The key to the 100,000-year cycle is found in the ground itself. To understand why the ice became so durable, we must examine what supported it. Long before the Great Ice Ages, the continents of North America and Europe had very different surfaces. They were coated with a thick, extensive layer of loose soil, weathered rock, and ancient sediment. Geologists call this regolith. It represented the accumulated debris of countless millennia of erosion. When the first glaciers appeared roughly 2 million years ago, they rested upon this regolith. Picture loose soil as a bed of tiny rolling spheres. It offers little resistance. As ice sheets expanded over this surface, they remained highly mobile. They slid smoothly, they spread widely and rapidly, and because they were thin and constantly shifting, they were easy to destroy. When the 41,000-year tilt cycle brought slightly warmer summers, these thin, unstable ice sheets collapsed quickly. They melted away. But glaciers are not simply frozen water, they are nature's most formidable bulldozers. Every advance and retreat during those early cycles turned them into colossal sheets of sandpaper. They scraped, they carved, they pushed the regolith into the seas. For 1 million years, the ice gradually peeled the continents bare. Then around 1 million years ago, the process reached completion. The loose, unstable soil had been removed. The Canadian Shield and the Scandinavian ranges were scoured down to solid crystalline bedrock. The physics of the ice transformed instantly. The glaciers no longer rested on a smooth, slippery foundation. They sat upon rough, high-friction stone. The ice adhered. It clung to the rock. This increased friction prevented the glaciers from sliding freely. Instead of spreading outward in a thin sheet, they began to build upward. They rose layer upon layer, becoming denser, sharper, and increasingly frigid. They transformed into towering citadels of ice. Their immense thickness and low temperatures gave them a new kind of defiance. When the 41,000-year tilt cycle returned with its warming phase, these stubborn ice sheets simply refused to respond. The warmth of summer could not penetrate the fortress. The ice endured the faint heat and continued to expand. It began to ignore the usual rhythm. It waited. It grew for another 40,000 years, then another, until it reached a scale so unstable and colossal that only the strongest orbital influence of all the 100,000-year eccentricity cycle could finally dismantle it. The planet shifted its rhythm because it had transformed its outer layer. By stripping away its own soil, the Earth unintentionally created a trap, giving the ice the chance to grow into the giants that shaped the past 1,000,000 years. But even giants eventually reach their limit. And when the 100,000-year cycle arrives, the end of an ice age is not a gentle transition. It is a collapse. For 90,000 years, the ice accumulates. It grows through a slow and disciplined process, steadily removing water from the sea and heat from the atmosphere. But its ending is anything but slow. It abandons patience. It collapses. In paleoclimatology, this moment is not described as a warming. It is called a termination. The term carries a sense of force, and it fits what happens when the 100,000-year cycle finally lines up to deliver heat. The orbital stretch increases, the tilt becomes greater, and the wobble turns the North Pole toward the Sun. The ice fortress is assaulted from every direction. Solar energy strikes with intensified strength. Carbon dioxide rising from the warming southern oceans fills the atmosphere. The ice sheets, now dangerously tall and unstable, begin to decay. They do not melt away gently. They fracture. Immense lakes of meltwater, some comparable to inland seas, gather on the glacier surfaces. Pressure builds until the ice gives way, releasing millions of gallons of water down vertical channels known as moulins, all the way to the bedrock below. This water becomes a lubricant. The friction holding the ice in place disappears. Entire regions of the ice sheet destabilize. They slide into the ocean in fleets of icebergs, a phenomenon referred to as a Heinrich event. These fleets grow so immense that they clog the North Atlantic, disrupting currents and reshaping weather patterns across the globe. On land, the destruction is overwhelming. Ice dams restraining lakes weighing trillions of tons give way. The resulting mega-floods exceed anything imaginable in modern times. Walls of water hundreds of feet high sweep across the terrain, stripping soil to the bedrock within days. The scablands of Washington state remain as evidence of one such explosive outburst. And the ocean too responds violently. It does not rise little by little. It surges during episodes known as meltwater pulses. Global sea levels can jump several meters within a single human lifetime. Continental shelves vanish beneath the waves. The land bridges of Beringia and Dogland disappear beneath rising seas. The world's map is redrawn with breathtaking speed. Islands emerge. Peninsulas are cut away. This is the Great Melt. It is the steepest rise on the sawtooth pattern of Ice Age cycles. 90,000 years of winter are erased in just a few thousand years of unruly water-filled and explosive spring. And when the waters finally calm, when the ice retreats to the poles and the shorelines settle into place, a transformed world comes into view. It is warm, humid, and remarkably steady. It is a world that allowed a once roaming primate species to stop moving, to plant crops, and to build shelters. The violent surges of meltwater eventually ceased. The oceans stopped climbing. The coastlines, which had marched inland for ages, at last became stable. Then around 11,700 years ago, the Earth did something it had not done in ages. It became calm. For the previous 2 million years, the climate had acted like a roller coaster. It swung wildly between freezing lows and scorching highs. Weather brought relentless and unpredictable shifts. A person born in 1 century might know a flourishing grassland, while their grandchildren could find themselves in a barren, dust-filled landscape. But the new epoch, the Holocene, unfolded differently. When you study the climate record for the past 10,000 years, it does not form a jagged pattern. it appears almost perfectly level. It is a broad plateau of warmth, a long, steady, and golden afternoon in the planet's story. This stability represents the Holocene exception, and it stands as the single most critical geological reality in the entire story of our species. Think about the timing. Anatomically, modern humans have existed for at least 300,000 years. For all that time, we possessed the same brains, the same hands, and the same potential for language and innovation. Yet during 95% of our history, we created nothing lasting. We did not sow fields. We did not construct cities. We lived as nomads, small groups of hunters following migrating herds, always responding to a world that never stopped shifting. We were intelligent, but we were ruled by the chaos of the Milankovitch cycles. A society cannot cultivate farmland when rainfall patterns transform every generation. A community cannot raise a city when the ocean rises 1 meter every 10 years. And then the Holocene arrived. The climate settled into a narrow and dependable band. The rains became steady. The seasons became predictable. And immediately across every continent, humans stopped fleeing. We planted the first seeds in the Fertile Crescent. We nurtured rice in China. We raised temples throughout the Americas. We invented writing mathematics and the foundations of civilization. Everything we are and everything we have built, from the earliest sun-dried bricks to the International Space Station, rests upon this one delicate pillar of climate stability. We are the offspring of the Holocene. But when scientists examine this golden era in detail, they grow uneasy, because compared with earlier warm intervals, the previous breaks between ice ages, the Holocene appears unusual. Typically, interglacial periods are brief. They rise sharply in warmth, remain stable for only a few thousand years, and then swiftly begin the long descent back into glacial cold. According to every rule of the Milankovitch cycles, the Holocene should have ended thousands of years ago. The peak warmth has already passed. The orbital alignment responsible for the great melt has diminished. The 65th parallel receives less sunlight. By the cosmic timetable, the celebration should be finished. The ice should be returning. The glaciers should now be advancing from Baffin Island and Norway, yet they are not. The extended summer persists. The planetary pendulum seems frozen. And this brings us to the most disturbing question of all. Is this stability truly natural, or have we without any intention disrupted the clock? If we were faithfully following the cosmic instructions, obeying the gravitational rhythms that governed Earth for the past 1 million years, our golden age would already be over. We are living on borrowed time. When astrophysicists analyze Earth's present orbital configuration, the numbers are unmistakable. The Milankovitch machinery is shifting toward colder conditions. The axial tilt of Earth is decreasing. The planet is gradually becoming more upright, reducing the strength of its summers. The wobble, the precession of the equinoxes, has pushed the northern hemisphere's summer farther from the sun. The orbit is evolving. By every mathematical standard, the interglacial window has closed. The solar energy striking the crucial Arctic threshold, the 65th parallel north, continues to fall. In fact, the amount of sunlight reaching the Arctic today nearly matches the level from 115,000 years ago. And 115,000 years ago marked the beginning of the last ice age. So where is the ice? In truth, the planet did attempt to return to the cold. It tried to follow the expected pattern. Around 5,000 years ago, the peak warmth of the Holocene ended. Earth entered a stage geologists call the neoglacial, a slow and uneven cooling trend. Tree lines in Siberia withdrew southward. Glaciers in the Swiss Alps and Norway reawakened and began sliding down their valleys, entombing ancient forests that had flourished during earlier warmth. This cooling reached its height only recently. We know this period as the Little Ice Age. From the 14th to the 19th century, the planet chilled noticeably. It was an era when the Thames River in London froze so solid that people held festivals on the ice. It was an era when Viking settlements in Greenland, which had cultivated green meadows for centuries, collapsed as expanding sea ice cut them off. It was an era marked by famine and widespread crop failures across Europe. This pattern was not accidental. This was the onset. It marked the first uncertain movement toward the deep descent into the next glacial peak. The planet was reacting to the Milankovitch signal. The reflective shields were beginning to assemble. The oceans were preparing to draw in vast amounts of air. The entire system was behaving exactly the way it always had, and then without warning, the cooling ceased. In the span of a geological heartbeat, the pattern reversed. The downward slide into cold did not simply pause, it fractured completely. The temperature did not merely steady, it surged upward. The glaciers that had pushed forward during the Little Ice Age did not just shrink, they started to disappear. The Arctic sea ice, which should be thickening at this very moment, began to thin out instead. The cosmic clock continues to tick. The pull of Jupiter continues to act. The tilt continues to decline. The message of approaching winter is still being broadcast clearly across the solar system. But the Earth no longer responds. Something has disrupted the mechanism. A new force has entered the system. A force powerful enough to overpower the pull of the giant planets and the alignment of the Sun. And this force did not originate in the heavens. It rose from the ground. It emerged from the flames created by a single species that discovered how to unseal the carbon of the Carboniferous. The force that halted the ice did not descend from the sky. It rose from beneath our feet. For millions of years, the carbon of ancient landscapes had remained securely buried. The forests of the Carboniferous, the microscopic life of the Jurassic seas, all had been locked away in darkness, transformed into coal and oil. They were the dormant spirits of the planet. And then, in a geological instant, one species chose to awaken them. We refer to it as the Industrial Revolution. But in the language of the Earth, it was a burst of carbon. We unearthed the fossilized light of 300 million years and returned it to the air in only 2 centuries. We took the carbon cycle, a process that normally unfolds over thousands of years, and accelerated it to the tempo of a detonation. The impact on the Milankovitch system was immense. Remember the fragile equilibrium needed to trigger an ice age. The orbit elongates to cool the planet. The tilt decreases to weaken the summer heat. But these influences are gentle. They depend on an atmosphere thin enough to allow warmth to dissipate. Researchers have identified a precise threshold, a critical number for the start of a glacial period. To begin an ice age, atmospheric carbon dioxide must fall below 280 parts per million. For the past 10000 years, we hovered exactly at that boundary. The planet was prepared. The entrance to the ice was cracking open. But then we began to burn. We pushed the value past 280, then 300, then 350. Today we are moving beyond 420 parts per million. We have not simply adjusted the thermostat, we have shattered it. The level of heat-absorbing gas now present in our air is higher than at any point in at least 3 million years. We have created an atmosphere resembling that of the Pliocene epoch, a time when the continents of the Americas were still divided and forests grew near the South Pole. This massive veil of carbon acts like a barrier. It intercepts the faint summer sunlight, traps the warmth, and refuses to let it escape. It completely overrides the cooling message sent by the orbit. The pull of Jupiter continues. The axis continues to shift, but none of it holds significance now. The signal has been drowned beneath the volume of our emissions. We have accomplished something no species before us has ever achieved. We have cancelled an ice age. This is literal, not symbolic. According to orbital patterns alone, the Earth should have been preparing to enter its gradual descent into the next glacial peak within the next 1500 years. The great ice sheets should be strengthening as we speak, but because of the carbon already released, that outcome has vanished. The next ice age has been delayed, perhaps 50000 years, perhaps 10000. Some projections warn that if we burn all remaining fossil fuels, we will not merely delay the ice. We will eliminate the cycle entirely. We could drive the planet into a heat state so extreme that the ice sheets of Greenland and Antarctica collapse, fully erasing the reflective shields of the system forever. We have stepped into a new geological era. The Holocene has ended. We exist now within the Anthropocene, an age in which the primary geological force is not the volcano, not the meteor, not the orbit. It is us. We have taken hold of the controls of the planetary engine. We have stopped the clock. Yet we do not truly comprehend the machine we are steering, and we have pressed the accelerator to its limit. We have secured a prolonged summer. But the unresolved question remains: what becomes of a world built to freeze when it is compelled to burn? We have obtained a delay, a long summer. On the surface, it may appear to be a victory. Humanity is fundamentally a tropical species shaped by the warmth of Africa. We possess no fur, no insulating layer of fat, and we instinctively recoil from the cold. Preventing the glaciers from returning, keeping the immense sheets of ice from crushing our northern cities, can feel like the ultimate triumph of intelligence over geological forces. But this sense of triumph is a perilous illusion. We have not simply stopped the pendulum, we have severed the cord entirely. And a world without its pendulum does not naturally settle into equilibrium. it drifts into disorder. By driving carbon dioxide levels beyond anything seen in the last 3 million years, we are pushing the planetary vessel toward a condition scientists refer to as hothouse Earth. In such a state, the feedback loops previously described the mirrors and the thieves begin to operate in reverse. As the Arctic heats, its white reflective ice disappears, exposing the dark ocean that lies beneath. This darker surface absorbs additional warmth, which accelerates the melting even further. The mirror is destroyed. As the permafrost of the far north softens and breaks apart, it releases the carbon long trapped in frozen soil over countless millennia. The thief returns what it once hid. The planet starts to amplify heat just as powerfully as it once amplified cold. If this trajectory continues, we are not approaching a stable, warm Holocene. We are heading toward a revival of the Eocene. Envision a world perhaps only centuries or millennia away, in which the polar ice caps have completely vanished. Antarctica, once a white continent, becomes lush and green. Forests of beech and fern spread across the edges of the Southern Ocean just as they did 50 million years in the past. The Arctic Ocean transforms into a lukewarm, marsh-like sea filled with algae and abundant life. In such a world, sea level is not measured in inches. It rises by 70 meters above its present height. The coastlines we know today, from Florida to Bangladesh to the Netherlands to the vast deltas, become memories submerged beneath the deepening ocean. But the deepest cost of this extended summer is neither the rising heat nor the swelling seas. It is the disappearance of rhythm. The Milankovitch cycles, despite their harshness, offered a pattern. They created a dependable, repeating stability. The ecosystems understood these rules. Forests moved north and then south. Animals evolved and adjusted accordingly. Within a hothouse Earth, that ancient script is destroyed. Weather turns violent and unpredictable, driven by the immense thermal energy locked within the air. Storms grow to planetary proportions. Droughts settle over continents as if they belong there. The ocean currents, the mighty conveyor belts shifting heat around the globe, may weaken or even reverse. We have exchanged the steady, rhythmic ticking of the cosmic clock for the erratic, burning tremor of a malfunctioning machine. And yet, the Earth itself, its stone, water and air, remains patient. The massive carbon pulse we have unleashed is enormous, but it is not endless. The fossil fuels will eventually be exhausted. The pulse will fade, and the slow geological mechanisms will begin the long process of restoration. This will require time, an almost unimaginable span, 10,000 years, 50,000 years, perhaps 100,000 years. The silicon-rich rocks of the mountains will gradually weather, interacting with the carbon dioxide dissolved in the rain, stripping carbon from the sky, molecule by molecule, delivering it back to the sea where it becomes locked inside. Limestone. The fever will subside, the atmosphere will lighten, and once the carbon has finally disappeared, the ancient signals will persist. Jupiter's gravity will continue its pull. The axis will continue to tilt. The sun will continue to cast its light across the far Arctic. The Milankovitch cycles have not vanished. They are simply waiting their turn. They are the steady heartbeat of the solar system, pausing only until the clamour of the Anthropocene fades enough for them to continue their ancient rhythm. The ice will come again. It may require 500,000 years, but the towering white masses will inevitably return. For the Earth is not a fixed and motionless body. It is a dynamic and responsive system, and we are nothing more than a brief rise in temperature during its long and drifting slumber. Let us step back. Let us lift away from the crust of the Earth. Let us rise beyond the haze of the Anthropocene, past the dissolving glaciers, beyond the constant hum of our societies. Let us move outward into the quiet darkness of space to a vantage point where the Earth hangs like a small sphere of blue and white adrift in emptiness. And now, imagine accelerating time. If we watch the last 1 million years of our planet unfold in a rapid sequence, we would not witness a simple stone. We would not see a still and unchanging diagram. We would observe something alive. We would watch the immense pale crown of the northern pole swell and slide downward like spilled milk, covering Canada, engulfing Europe, transforming the globe into a world of white. Then we would watch it recede, retreating toward the ocean, uncovering stretches of green and brown terrain. Spread, withdraw, spread, withdraw. The pattern repeats itself every 100,000 years. It looks remarkably like a chest lifting and lowering. It resembles a lung filling and releasing. These glacial eras are not an illness. They are not an accident. They are the breath of the Earth. For 1 million years, the planet has been inhaling and exhaling. It draws in the cold and releases the warmth. It pulls the sea onto the continents as frozen mass and then returns it as liquid again. This pattern is the very pulse of the solar system. It is the influence of Jupiter gently pulling on our orbit. It is the tilt of our axis bowing toward the sun. It is the quiet silver mechanism of the universe guiding the rhythm of our world. And we are beings born in the warm exhale. Our civilizations, our memories, our entire shared experience have unfolded during the short, mild interlude between two planetary breaths. We belong to the interglacial. We assume endless summer simply because our individual lives are so brief. But the Earth moves according to its own scale. It does not track time by years or centuries or the rise and fall of rulers. It marks time through cycles, through shifts, through orbital paths. The stillness of the Earth is not a void. It is patience. It is the patience of a mountain awaiting the return of the ice that will grind it into grains. It is the patience of the sea preparing to reclaim the land. It is the patience of a world that knows with mathematical certainty that the cold season will arrive once more. The carbon we have forced into the atmosphere is a disturbance. It is a fever, but a fleeting one. The stone will absorb it, the water will conceal it, and in time the heat will fade. When that moment comes, the great celestial gears will continue their motion. The axial wobble will continue to shift the sky. The orbit will continue to lengthen into the darkness. The signal will remain, and the Earth gradually and quietly will begin another slow inhale. So as you rest tonight, wrapped in the gentleness of this long and radiant summer, remember the rhythm. Pay attention to the quiet. It is not a silence of death. It is the profound, steady and everlasting breath of the planet. Good night.